Welcome to a brief introduction to inferential statistics. This is the core of what statistics are. So I want you to imagine a simple thing. If you flipped a coin 10 times, what would happen? How many heads would you get? And now most of you would say, rightfully so, 5 heads, 5 tails, 50-50. Now, if I said to you, what? Well, I got 6 heads. Would you think that's outrageous? And most of you would say, no, that's reasonable. 6 heads is within what we'd expect by chance alone, or even 7 heads, or 3 heads, or 4 heads. But when we get outside of that, what is the point at which you think we got a weighted coin and I'm cheating you? Now, some of you might say 8 heads and some might say 9. And what we're doing with inferential statistics is trying to figure out where that cutoff is. And what I've used to describe this basic foundation of inferential statistics is what's called the binomial distribution. And you don't need to remember that, but it's normally distributed. What we have is the probability on the y-axis, how often it's going to be, and the number of heads on the x-axis. And most of the time, we're going to get 5 and 5. But sometimes we're going to get 6, 7, 8, 9, and even 10 heads can happen. It's rare, but it could happen. 4, 3, 2, 1, and 0. 0 is rare. It could happen. And the probability of each of these goes down. So the likelihood of getting them drops. And now what you see here is this kind of looks like a normal distribution, a very specific type of distribution. So this is, again, a binomial distribution, and there's all kinds of distributions when we're trying to determine inferential statistics. And what we know here is that these things in the middle occur a lot. They're very likely. These things out in the tails are not likely. And how likely are they? That's the big question in inferential statistics. That's what we're trying to figure out. Now, in inferential statistics, in the behavioral sciences, we're taking bets. That's essentially what we're doing. We're trying to figure out how likely is something to happen versus how unlikely is something to happen. And we're saying, if it's really likely, it's likely to do just, normal behavior. But if it's unlikely, something different has happened. So what we look at with this distribution, and I'm just going to redraw the normal distribution, and it's a terrible normal distribution. I'm terrible at drawing, but it'll help you do it, is how likely are things to happen and how likely are things not to happen. Now, again, this is the probability or frequency here, and the occurrence along the x-axis. And we're taking this bet. And we're saying if something is somewhere in this big area, it's likely to occur, it's normal. It's something that happens. If it's out in the tails, it's something rare. And we're willing to take a bet that it's something that's beyond what we'd expect by chance. So what's that mean? And I'm going to change examples now from the coin flip to betting at Turning Stone Casino. So if you go to the casino and if somebody said to you, there's a 50-50 chance you're going to win, how much would you put down? Would you be willing to bet? My suspicion is the question is not a lot for a 50-50 chance of winning. What if I said 60-40? What if I said 75? Would you be willing to bet $100 on a 75% chance of winning? Maybe, maybe not. Some of you, depending on your financial situation, maybe, maybe not. 80%, $100, if you're 80% likely. What about 90% likely to win? You're likely to double your money. Well, a lot of you would take that bet. In the social sciences, we want to be 95% sure. We have to be very confident. This is called our confidence or our confidence interval. We want to be 95% sure we're right when we're taking that bet. Okay, and so that means this middle part is 95% sure. We're taking a bet on 95% of the time that would happen. And that means there's 5% off in these tails. Well, there's two tails, so there's 2.5% here and 2.5% here. So that's the probability of error. Our p-value is less than 0.05, or our probability of error is less than 5%. And now you'll see here, we're 95% sure, we have a 5% chance of error. And that's the bet we're willing to take. We're not willing to take a bet until we're 95% sure that something is right. So let me give you a very specific example. Now, let's say we have a test where we're doing our dissertation and we're comparing leadership in women to leadership in men. And we're saying women are more empathetic leaders than men. And our statistical test says P equal to 0.13. Well, that says our probability of error is 13%. And that's saying, well, women and men are not different. We're not willing to take that bet yet. We're going to say that women and men are, we're not saying they're equal. Wording's different. Are not different in empathy. Okay, because we haven't reached that 95% confidence yet. We're not 95% sure. What if our statistical test says P equal to 0.02? Well, in this case, we are 98% confident. Okay, so up here, we're only 87% confident. And now down here, we're 98% confident. So here, we're willing to take that bet and say women and men are different in empathy. So we want to be really sure before we make any determinations about saying something's different. So when you're reading your articles, this p-value is absolutely essential because that's telling you p less than 0.05 equals statistically, these are very specific words, significant, p greater than or equal to 0.05. It's not significant. It's got to be p less than 0.05. So 0.05 equals, the wording is very specific. It is non-significant. It doesn't mean it's not significant. Not significant means not meaningful. Non-significant means it's a statistical term that says not statistically significant. So when it's statistically significant, something happened that's more than we would expect by chance. Could we be wrong? Yes, we have a very small proportion of error. We could be wrong. We're not sure. So now statistical significance, our p-value, and remember that thing about Greek letters that I already posted. Alpha is our theoretical idea about statistical significance that we've set ahead of time. And we use alpha less than 0.05 in the social sciences. P is our calculated based on our data. And we use, of course, P less than 0.05. And they really mean the same thing. This is just your theory, and this is just your practical result. This is based on data. This is based on our pre-existing idea. So alpha and P. Now, if we have P less than 0.05, it is statistically significant. Here's the rub. It can't be really significant or sort of significant or almost significant. Now I'm going to put an asterisk there because there is a little side note that I'm going to talk about because some of your articles are using a fancy term and getting away with a little fudge factor. Significant or non-significant. There's no sort of, there's no really, there's not at all. It's just one or the other. It's a binary outcome. If something is P equal to 0.000001, it doesn't mean it's a really strong effect. It just means it's statistically significant, period. Nothing else. So the second thing that you'll see in your articles is an effect size measure. So I'm going to use something that we haven't talked about, but is in the next video, the t-test. The t-test will give you a t with some level of degrees of freedom, let's say 18, and then it'll give you a value equals 2.46. That's your result of your t-test. And again, wait for the next video. Then it'll say P less than 0.05, or it'll give you the exact P value. And then it'll say D equal to and give you some value. Okay, this is your statistical significance. This, after the p-value, whatever it is your effect size. And I'll be putting something on Blackboard that shows the importance of effect size. It's actually already there. The importance of effect size measures and how to read effect size measures. Effect size measures tell you if it's small, medium, or large effect. This is where you get the meaning. So you could have a P equal to 0.049. It can be statistically significant in a large effect size. And the difference is P values are heavily dependent on sample size. Okay, bigger samples, you're more likely to be statistically significant. Smaller samples, you are less likely to be statistically significant, regardless of how big the effect is. Now, a lot of people say your effect size measures, whatever they are sample size free. And I disagree with that. I say they're far less dependent on sample size. So that's why effect size measures are so important. And again, look at that chart, because for effect size, it depends on the statistical test. For T, you use Cohen's D. For chi-squared, you use a phi coefficient. For ANOVA, which is abbreviated with an F, you use either the eta squared or omega squared. Usually SPSS gives you eta squared, so most people use that. For correlation models, which are generally R, so that's multiple regression, correlation, bivariate regression, path analysis, it's the R squared. So these are the ideas that effect size measures. And again, look at that chart, which is on Blackboard, and it'll explain to you how to interpret all these different effect size measures. So you can then make the determination about whether it's small, medium, large. Large means it makes a huge difference. It's an important outcome that you found. Medium means, well, there's lots of things that predict this. You found one of the good ones. Small means, yeah, it does predict it, but it's not super important. So that is a primer to inferential statistics.